Prior to 2017, machine translation relied on recurrent neural networks, or RNNs, architectures where the output from the previous step feeds into the current step. The most common variant was the long short-term memory network, a system designed to capture long-range dependencies by processing words one after another. This creates a strict mechanical constraint. The model generates a sequence of hidden states, mathematical representations of the text, where ht is a function of the previous state, ht-1. Because step 10 depends on step 9, the system must factor its computation strictly along the sequential positions of the input. This sequential requirement physically precludes parallelization within training examples. You cannot calculate the end of a sentence until you finish calculating what came before it. As sequence lengths grow, this becomes a severe bottleneck. Memory constraints limit the model's ability to batch examples together, causing computational efficiency to crash. The more data you feed the system, the more the sequential logic slows it down. Engineers attempted to address this with factorization tricks to simplify the math, or conditional computation. These methods improved performance, but the underlying sequential constraint remained unbroken and perfectly intact. Achieving true contextual understanding at scale required a complete departure from the sequential processing paradigm. In 2017, Google researchers published Attention is All You Need, a paper proposing an architecture that dispenses with recurrence and convolutions entirely. Convolutions are mathematical operations that process data in local windows. While faster than RNNs, they still struggle with long-distance dependencies. The researchers proposed relying strictly on a mechanism called self-attention. Self-attention relates different positions of a single sequence simultaneously to compute a representation of the entire text, drawing global dependencies in one pass. This chart compares computational complexity. Recurrent layers require ON sequential operations, meaning steps grow linearly with text length. Self-attention requires O1 operations. The number of sequential steps remains constant regardless of sequence length. If successful, this shift reduces the time required to connect any two concepts in a text, from a lineal crawl to a constant time instant. If the model has no recurrence and processes every word simultaneously, it loses the ability to perceive the order of words. The dog bit the man and the man bit the dog look identical to the math. To solve this, the model first converts raw tokens into continuous 512-dimensional vectors. This fixed dimensionality is known as D-model. The researchers then introduced positional encoding to restore the sense of sequence. To inject positional information, we use a progression of sine and cosine functions. Wavelengths range from 2π to 10,000 times 2π. These waves are summed with the input embeddings, effectively tagging each word with its exact location. While the researchers tested learned positional embeddings, they chose these sinusoids because the periodic nature of the waves allows the model to extrapolate to sequence length longer than those it saw during training. This allowed the model to process massive blocks of text simultaneously, while perfectly preserving the spatial relationships of the grammar. Data flows into the scaled dot product attention engine. Queries and keys are multiplied to produce a compatibility score, determining focus. These scores are scaled down by the square root of the key dimension, then passed through a softmax function to create stable probabilities. This engine is a highly optimized parallel matrix multiplication that allows every word to instantly query its relevance to every other word in the sequence. Using only a single attention head forces the model to average its focus across the entire 512-dimensional space, which inhibits its ability to track multiple linguistic relationships at once. The solution is multi-head attention. The model linearly projects the Q, K, and V matrices 8 times. It runs the scaled dot product in parallel across these heads, then concatenates and projects them into final output values. Multi-head attention allows the model to jointly attend to different representation subspaces, meaning one head can track verb tense, while another tracks subject-object relationships. The complete architecture uses an encoder on the left, stacking 6 layers of multi-head attention and feed-forward networks. The decoder on the right uses a similar stack, but adds a middle attention layer to look back at the encoder's output. When generating the next word in a sequence, the model is auto-regressive. It uses previously generated words to predict the next one. This means the model must be prevented from cheating by looking at words that haven't been generated yet. We implement this using masking. Inside the self-attention calculation, future connections are set to negative infinity, ensuring predictions only depend on previous words. This assembled stack successfully replicates the power of complex encoder-decoder models using only attention mechanisms and feed-forward networks, completely eliminating the need for recurrence. Theoretical architecture is only useful if it works in practice. We need to see if a model that ignores sequential reading can actually master the structure of human language. This visualization of the attention heads at layer 5 reveals what the matrices actually learned. Notice how the model bridges a long-distance dependency between the verb making and the phrase more difficult. An RNN requires O of n sequential steps to traverse that gap. The transformer connects them instantly. We can also observe how individual heads divide the labor of grammar. These heads have learned to perform anaphora resolution, the process of linking a pronoun to its correct noun. The individual heads bind the word its accurately to both law and application. Complex syntactic and semantic structures emerge directly from the parallelized, multi-headed self-attention mechanism. The results were definitive. On the WMT 2014 English to German task, the big transformer achieved a BLEU score of 28.4. BLEU is a standard metric that measures translation quality by comparing machine output to human references. A score of 28.4 established a new state of the art, surpassing even the best ensemble models of the time. The model achieved this record at a fraction of the computational cost. Measured in flops, or floating point operations, an estimate of the total work performed by the hardware, the transformer required just 2.3 times 10 to the 19th power. The previous state-of-the-art ensemble required over 50 times more computation to reach a lower score. The architecture also excelled at English constituency parsing, a task that requires representing the internal structural hierarchy of a sentence. They outperformed nearly all previous models, despite having minimal task-specific tuning. By trading linear sequence modeling for constant-time matrix multiplication, the researchers successfully scaled deep learning to new heights. The transformer architecture successfully bypassed the sequential processing limit of deep learning, providing the mathematical foundation for the massive parallelization required in current artificial intelligence.